Hermitian matrix. So let us consider a matrix A, which is Aij m cross n, which is the order of the matrix. And if you find the conjugate and the transpose of that particular conjugate, that is A conjugate transpose, and if this matrix gives you back the original matrix, then we can say that A is a Hermitian matrix. Now this A conjugate transpose or A transpose conjugate, both are same. So whether you first take the conjugate and then you take the transpose, or first you take the transpose and then you do the conjugate, doesn't mean different. It means actually the same thing. And this have been given a special notation in linear algebra, which is theta. So whenever you see A to the power of theta, understand it is nothing but A conjugate to the power transpose or A transpose conjugate. So you can say this as to be the transposed conjugate of A, or you can also call this as to be your conjugate transpose of A. Fine. Now how can we say that this A conjugate transpose or A transpose conjugate, these both values are same? So let's see here. We have a matrix A which is 1, 2i, minus 3, 1 plus I. If we find A conjugate, of course this 1 will be 1 itself, the conjugate of 2i will be minus 2i, conjugate of minus 3 will be minus 3, and conjugate of 1 plus I will be 1 minus I. Fine. Now we have already found the conjugate of A. Now we have to find the transpose of this. So A conjugate transpose, that means we have to convert the rows into columns. So the first row will get converted into first column, second row gets converted into second column. So as you can see here, the final elements we have 1 minus 3 minus 2i and 1 minus I, which is nothing but this part. Okay. Now here as you can see here, so we have A, we have got this value. Fine. Now if you take the transpose first and then you take the conjugate, you will get the same thing. See here, this matrix and this matrix. Can you see both these matrix same? So whether you first find the conjugate and then you take its transpose, or first you find the transpose and then you do the conjugate, your final matrix is going to remain same. And hence we can say that whether you write this or this, it actually means this. Okay. Now let's say we have a matrix A which is 1, 2 minus I, 2 plus I and 1. We are interested to check whether this is Hermitian or not. So what is the logic to check Hermitian? I need to check whether the conjugate transpose becomes the original matrix or not. So first I will find the conjugate. So the conjugate of this will be 1. Then we have in place of 2 minus I, we have 2 plus I. In place of 2 plus I, we have 2 minus I and then 1. So here again, if you take the transpose, you will get this particular original matrix. So here as you can see, whether you are taking this conjugate and then you transpose, you are getting back the original matrix. And hence we can say that A to the power of theta is equal to A, and hence we can say that this matrix is a Hermitian matrix. Now you'll be asking, sir, do I need to find this conjugate and then I need to find the transpose and then I need to check? No. What you have to do is you have to apply the shortcut. The shortcut says that for Hermitian matrix, that means for any matrix to be a Hermitian matrix, these two conditions is mandatory to be satisfied. The first condition is the diagonal elements are always real. Okay, so the first condition is that you need to check whether the diagonal elements are real or not. If they are real, then go for the second. The second condition says the upper and lower diagonal elements are always conjugate pair. So let's see here. These two conditions we have to check here. So first condition is that see along the diagonal whether all the diagonal elements are real or not. So can you see all the diagonal elements are real? Yes, all are 1 and 1. So 1 is a real number, 1 is a real number. So this all the elements in the diagonal are real number. Second is upper and lower diagonal elements have to be conjugate pairs. So here as you can see, this 2 minus I is the conjugate pair of 2 plus I. And what is a conjugate pair? We have already discussed in the previous lecture. Okay, so first condition is satisfied, that is all the diagonal elements are real. Second condition is also satisfied, that is these non-diagonal elements or upper and lower diagonal elements are also conjugate pairs. So once these two conditions are satisfied, there is no need of doing all this. You can directly say that this is a Hermitian matrix. Now let's see what are the properties of Hermitian matrix. So now let us consider we have two different matrices A and B which are Hermitian matrices. So if they are Hermitian matrices, then we can say that A to the power of theta is equal to A, and also B to the power of theta is also equal to B. So the first property says that a to the power of n whole to the power of theta, you can also write this as a to the power of theta whole to the power of n. Of course, we can exchange the powers, and we know that a to the power of theta is what? A. So we can, in place of a to the power of theta, we can write a, and the n remains as it is. Fine. Now the second one, that is lambda 1a plus minus lambda 2b whole to the power of theta, we can break this in separate. So here we can write a lambda 1 a to the power of theta plus minus lambda 2 into 8 b to the power of theta. A to the power of theta is a and b to the power of theta is b, so we can write this. So we are getting this. So hence we can say that this lambda 1 a plus minus lambda 2 b is a Hermitian matrix. Now this power theta was also applied to this, but since this is a real numbers, this lambda 1 and lambda 2 are real numbers, so it doesn't have any effect on that. Third property, ab to the power of theta is equal to b to the power of theta into a to the power of theta, and we know that b to the power of theta is b, a to the power of theta is a, and hence this could be written like this. Moreover, ab plus ba whole to the power of theta could be written as ab whole to the power of theta plus ba whole to the power of theta. Now this ab whole to the power of theta, from this relation we can write like this, and from this relation we can write like this. Then b to the power of theta, we know that it's b, a to the power of theta it's a. You can break this out and you can simply write this, and hence we can say that this, if we are getting the original matrix back, and hence we can say that ab plus ba is a Hermitian matrix. Now similarly you can check for this, you will get the same result for this, that is with a negative sign of this. Fine. So we can say that this is a skew Hermitian matrix. This, we are not getting the original, we are getting a negative of the original, which we will see in the next lecture, that is a skew Hermitian. Okay, so this is a skew Hermitian matrix. Now Hermitian matrix over real numbers forms a subspace and vector space. Now since I have not introduce these two terms, subspace, vector space, so I'm not going to discuss it right now because you won't be able to understand, but for the time being please mug it up this statement, because sometimes in objective questions they ask the questions related to this. And for any square matrix you have, say all these matrices, that is a plus a to the power of theta, or a into a to the power of theta, or a to the power of theta into a, all these are Hermitian matrices. Now you'll be asking, sir, do I need to remember all these properties? Not at all. Suppose you have if you are asked to check whether a matrix is a Hermitian matrix or not, simply you need to find the power of that theta and you need to check whether that matrix is giving an original matrix or not. So let's say here, if you want to check whether this matrix is a Hermitian, then simply you need to put the power theta and check whether you are getting the final result as the original one or not. So here, as you can see, that we can simply distribute it. So a to the power of theta and this a to the power of theta whole to the power of theta. We know that a to the power of theta will be a. Why? Because this a is a Hermitian matrix, so we can write like this. And instead of a to the power of theta, also we can write a, and this theta comes here, and hence we got the same result. Similarly, you can do this analysis for this result as well and this result as well. Fine. Now if you have understood what is a Hermitian matrix, now one task for you, that is you need to tell whether this matrix is a Hermitian matrix or not. Okay, this P matrix is a Hermitian matrix or not. Okay, so please solve it and do comment in the comment box. See you in the next lecture. Till then, bye.